Welcome to this deep dive. Today, we're plunging into a really fascinating corner of the online encyclopedia of integer sequences. You know it, the OEIS. We're looking at A000308, which is called recursive product growth. Our mission really is to pull out the key bits about how it's defined and how it behaves, especially for you if you're studying number theory.
Yes, and what's so interesting here, I think, is seeing how a rule that looks quite simple on the surface, well, how it can generate numbers that just explode. It grows incredibly fast.
It really does.
It's a fantastic example, really, of these recursive definitions you find all over the OEIS.
Okay, yeah, let's unpack that. So the core definition, it's this recursive formula. AN1, AN2, AN3. So each term is the product of the three terms right before it. And it kicks off with A1, A22, and A33.
Right.
So what is it about using a product, and specifically of three terms, that makes it grow so much faster than, say, Fibonacci, which just adds, or even sequences multiplying just two terms?
Well, that's the crux of it, isn't it? That product of three. It's not like adding terms, which gives you sort of linear or maybe polynomial growth.
Right.
And it's not even just multiplying two terms, which gives exponential growth.
Yeah.
This triple product, it leads to something more like hyper-exponential growth. It just takes off.
Wow.
And that non-keyword you see in the OEIS entry, it stands for non-negative. That's actually quite important here.
How so?
Well, think about it. If any term hits zero, the product rule would mean all subsequent terms become zero. The sequence would just flatline.
Ah, okay.
And if terms could be negative, you get this wild oscillation between positive and negative, depending on how many negative terms were in the product. So non guarantees this consistent positive and just relentlessly upward explosive growth.
And you really see that explosion when you list out the terms. It starts innocently. 1, 2, 3, then bang, it's 6.
Then 36.
Right, 36, then 648, and it gets huge almost immediately. We're talking 139,968 next. Just as a concrete example, like you said, a 6, that's a A4, A3.
Which is 3663.
Exactly, 3663, which gives you that 648. You can really feel the power of multiplying those three previous terms.
That jump is quite dramatic. And this kind of growth, while it seems almost chaotic, it's actually very structured, which raises a deeper question. Is there some hidden order?
Ah, okay. Is there?
Well, yes. The OEIS entry actually gives an explicit formula. AN 2A001590 N1 3A000000. That formula is incredibly revealing.
Whoa, okay. That looks complex. For those of us maybe not instantly familiar with A00000000, so what exactly are those? And why is connecting them to A000008 such a big deal?
Excellent question. So A000000C, that's actually the famous Tribonacci sequence.
Tribonacci.
Like Fibonacci, but with three terms.
Precisely. Each term is the sum of the three preceding ones, usually starting 0, 0, 0, $1, then 1, 2, 4, 7, and so on.
Okay, so that's based on addition.
Right. And A000590 is a related sequence connected to the exponents of 2 involved there. But the fascinating part is how our sequence, A000308, which is built purely on products.
It connects so directly to sequences built on sums, like Tribonacci. It shows this really deep interplay between addition and multiplication.
How does that work?
It seems to be encoded in the prime factors. Here it's just the primes 2 and 3. Their exponents, dictated by those other sequences, A001590 and A000073, which are related to Tribonacci sums, perfectly generate our product-based sequence A000308.
So the structure of the sums in Tribonacci somehow dictates the structure of the products in A00000308 via these prime exponents.
Exactly. It shows how seemingly very different recursive patterns can be fundamentally linked. For you as a number theory student, it's a brilliant example of uncovering hidden connections.
So wrapping this up then, for you listening, A000030 isn't just some random string of big numbers. It's a really powerful illustration of recursive definitions, especially how using products and involving prime factors like 2 and 3 can just unleash this incredible growth. And understanding these, like the amazing work N.J. Sloan has done curating the OEIS, helps us map these, wild number landscapes.
Absolutely. This quick dive really just scratches the surface, but shows the surprises hidden in the integers. So maybe here's a thought to leave you with. If you imagine a real-world system, maybe something in biology or finance or even a complex network, growing according to a rule like A000308's recursive product growth.
Okay.
What kind of practical challenges, maybe computational limits or logistical hurdles, would that incredibly rapid scaling present? And maybe more interestingly, could understanding its underlying connection to something simpler like the Tribonacci sequence actually help us predict or perhaps even manage that explosive growth?